Today we will address the critical material challenge associated with high temperature hydrogen heating, especially targeting application up to 1000 and slightly more. The focus is on ensuring a element longevity when operating in extremely demanding reducing atmosphere such as industrial furnaces utilizing hydrogen. Our central theme is how material selection directly impact element longevity in this harsh reducing environment. So, as the core challenges are basically is the material longevity, and in these circumstances, maintaining the structural integrity and electrical efficiency of heating elements within the specified high temperature atmosphere. For the elements to survive and operate reliably when heating hydrogen gas, the material must simultaneously withstand both the high temperature load required and extreme reducing environment of pure hydrogen. And many times uh, when we are coming across this heating of hydrogen system also might have got a mm, lot of different type of this contamination also, and contamination may have a some part though it's a smaller but a moisture or carbon monoxide or carbon dioxide and as well as nitrogen, because such systems are basically reducing a slightly carbon oriented material is getting processed, and at the same time the downstream system which are not 100% safe to take care of all moistures. Thus, the main challenge here is that we have to handle these heating system with 100% hydrogen, but at the same time there is a bit contamination also. So, the core challenge is maintaining the structural integrity and the electrical efficiency of heating element within the specified high temperature atmosphere. Now, for the element to survive and operate reliably when heating hydrogen gas, the material must simultaneously withstand both the high thermal load required and extreme reducing environment of pure hydrogen. Now, there are three keys requirement, especially in this for rather we can say successful material selection. First, the material must handle the maximum permissible temperature. Since the hydrogen gas temperature is 1000 degrees centigrade, the element itself must run significantly hotter, requiring a material capable of at least 1200 degree or higher element temperature in a pure hydrogen environment. Now, second point is about the we can say is oxide stability. So, oxide stability is basically forming a dense oxide layer that adhere well and resist gas diffusion to guarantee long operating life. And finally, the third point is the material need high mechanical strength, particularly sufficient creep strength to prevent deformation like bunching or sagging under high thermal load. We primarily utilize two main type of metallic resistance heating alloys, iron chromium aluminum or FeCrAl and nickel chromium or NiCr. We can say that the required operating temperature for hydrogen gas is 1000 degrees centigrade, meaning the element must be designed to run much hotter than this to meet the heating objective. As we have discussed earlier also, The critical failure modes, we seek to mitigate our creep deformation, scaling, and many other like yield strength also. Now uh, coming to this slide, which elaborate on how the advanced material, that is APM type A1, which can withstand the highest temperature. Maximum permeable element temperature in hydrogen is 1400 degrees centigrade. Similarly, standard is 1300, and nickel chromium high grade or nicrothal, we can say, is 1250. So coming to this information, our next slide is on the scientific data, which sensitize the alloys and its compatibility as far the environment is concerned. FeCrAl alloys, that is ferro, chromium, aluminum alloys, are highly recommended for high temperature hydrogen heating because they provide a much higher maximum operating temperature and a significant longer life. That is 2 to 4 times that of a nickel chromium material, which are just we have shown in the preceding slide in row number 3. The superior performance of FeCr aluminum element is attributed to the formation of an excellent non-spalling oxide layer on the surface, which is dense and resilient to gas diffusion, and this integrity minimizes the scaling or the release of impurities into the process. Now, for the critical projects involving high temperature hydrogen, selecting the most advanced ferrochromium aluminum resistance material, especially the powder metallurgy alloy, that is APM, is recommended. And these alloy offer improved hot strength, resulting in much better form stability, which reduces the need for element support and prevent bunching and creep. Advanced ferrochromium aluminum alloy have a creep strength, and they have got a slight contribution of the molybdenum, which gives these elements, setting elements, a better creep and yield strength also. So when these elements are getting utilized under a tremendous load, the longevity of such type of elements remain exist due to better creep strength. And now so we are here, it is one of our summary. The longevity benefit are substantial. Life expectancy is at 1000 degrees centigrade. Furnace temperature is more than double that of a nickel chromium wire, as we have discussed also, when used in a specific element system. Furthermore, the protective aluminum oxide film that form act as an extremely efficient barrier that we have already mentioned against a high carbon activity. These provide a high resistance to carbonization, which is critical, and if hydrogen is mixed with carbon bearing gases, such type of element can take care of such situation. Now, beyond the material type, optimizing design significantly impact life. Prioritizing the selecting thick material as element to thickness. Uh, uh, we can say that thicker wire or strip supplies more alloying elements per surface unit, which is necessary to regenerate protective oxide layer. For maximum surface load, design that allow for freely radiating elements such as the rod bend ROB type or corrugated wire strip elements are optimal. For enhanced longevity and control, the use of seamless extruded radiant tube like APM tube is highly beneficial. These tubes isolate the element from the gas flow, leading to improved operation and superior resistance to carbonization. Crucially, because they are seamless, these tubes eliminate potential welded failure points, and their non-spalling inner surface prevent contamination of the elements or the process gas. A key precautionary step is avoiding certain alloy in specific environment. Nickel chromium material should not be used in the furnace containing carbon monoxide. Protective gas atmosphere. The reason is the risk of green rot developing in the temperature range of 800 to 950. In contrast, ferrochrome aluminum alloy are superior and recommended for industrial furnace used in such complex reducing environment. A mandatory protocol for all ferrochrome aluminum elements operating in complex atmosphere uh, is pre-oxidation. This must be performed in air at 1050 degrees centigrade for 7 to 10 hours prior to use in reducing environment. This establishes the protective oxide layer that resists gas diffusion. Furthermore, regular re-oxidation should be carried out at suitable interval to maintain the integrity of this protective layer. Finally, advanced electrical control equipment such as thyristor must be employed to provide an even temperature and minimize rapid temperature fluctuation, as this fluctuation significantly reduce element operating life. So, to summarize our key recommendations for successful high temperature hydrogen heating project: first, prioritize advanced material selection. Choose powder metallurgical ferrochromium aluminum alloy APM for their superior hot strength and a stable non-contaminating oxide layer. And in addition to these, APM T can be selected where the some molybdenum part is participating, which are much better for withstanding the creep resistance and yield strength also higher. So APMT is much better. Secondly, we have to ensure the pre-oxidation. Implement the mandatory pre-oxidation schedule that we have already discussed, that is this is to be performed in air for 7 to 10 hours before installation and use for all ferrochrome aluminum element. Third is the to optimize the element geometry. Utilize freely radiating element designs, ideally mount inside the seamless extruded radiant tube for maximum protection. At the same time, we also need to see that contamination of this hydrogen gas should be free from nitrogen or carbon monoxide, carbon dioxide and moisture.